In this question, we're asked to determine the stability, the diamagnetic or paramagnetic nature, and the bond order for several different diatomic species. Sometimes they have different charges. So if we look at the valence electrons interacting for fluorine and oxygen, what we essentially have is an orbital diagram, a molecular orbital diagram that looks like this. We have a sigma 2s, a sigma star 2s, a sigma 2p, a pi 2p, a pi star 2p, and a sigma star 2p. And if you look at a previous video linked in this list, I go through this in detail for how we figure this out for O2. So, when we do this, we now need to add the electrons. Well, how many valence electrons? I only did it for the valence shell. So how many valence electrons are in F22+? Well, each fluorine has 7 times 2, which is 14. Because it's plus, there are 13 electrons. Fill them in, starting at lowest energy level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 electrons in here. This says, is this molecule stable? This is F2 plus is probably not something I would consider as stable. What this really means is bond order greater than 0. So if the bond order is greater than 0, it's stable. So in order to find this question, we need to find the answer to this question first. But be careful with the word stable. I would not say that F2 plus is a stable molecule, but it may have a bond order greater than 0. So bond order is equal to bonding electrons minus antibonding electrons divided by 2. So first thing we need to do for this particular one, in this case, is figure out how many bonding electrons there are. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bonding electrons minus, how many are in the starred orbitals or the anti-bonding orbitals? 1, 2, 3, 4, 5. And then divide by 2, and what you get is 3 over 2, or 1 1/2. So it's 3 halves. If you were to look at this being stable, again, not very stable, but the bond order is greater than 0, so we'll say yes. Now it says, is it paramagnetic or diamagnetic? Well, diamagnetic means that all the electrons are paired. And if you notice here, there is at least one unpaired electron. So this species is paramagnetic. You can repeat this for oxygen. What you're going to find is that it is stable, it is paramagnetic, and it has a bond order of 2. You would just put in the 16 electrons of the 12 electrons of the oxygen. So essentially, you would be missing that 1 electron there. Notice that this is for valence electrons only. In the case of lithium, we have the sigma 2s here, and the sigma star 2s, and we have Li2 minus. And we're only counting valence electrons. So lithium has 1 valence electron, so 2 of them have 2 valence electrons, and because it's minus, there's 3 electrons. Note that we won't use any of this 2p because lithium doesn't have a 2p orbital. There's not enough electrons. So here we can put in our 3 electrons, 1, 2, 3, and we can figure these things out. For the bond order, it's 2 in the bonding orbital minus 1 in the antibonding orbital divided by 2, which is 1 over 2, or 1/2. This is paramagnetic because it has an unpaired electron. and the bond order is greater than 0, so I guess this is stable.